Again, thank you for having me, Yandex and Tabula here. And this is loud. What I do at Lightricks is I run the research department. We do all kinds of things. A lot of them you'll see here. And I'll talk a little bit how AI is helping us actually be creative, because I don't think AI is that creative, not yet. Sorry. So you probably know this in like a different form, but to imitate was commendable, but to steal was unworthy. A lot of people say Picasso said a good artist steals, but a great artist or borrows and steals. And this is actually something that was published and people know was actually said, so I like it better. And this is actually something that I want to say, because a lot of times, neural networks and all the new machine learning models that we have are the best interpolators we have yet to see anywhere. They do amazing things, but they interpolate. They take the distribution and get into a small part of it and then interpolate between points in that distribution. They don't extrapolate that much, and a lot of times they pick specific things. And if you ever saw an artistic style transfer result and you see all the little patches coming from the original style input, so it's not exactly what I would call creative or anything like that, but it is art. It is art, just not that creative in my mind. But what I think AI is actually doing for us and really, really helping us is changing the way we do design and creativity and create just art in general. It helps us make complex things simple. Tedious can become very easy and effortless. All the things that you maybe, if you think about a creative person, a lot of times you think about like brainstorming and just jotting things out, but a lot of times it's really hard, tedious work. And also things that might be niche, just because they're hard, can become very common. So I'll start from complex becoming simple. I think one of the better examples of actually seeing creativity or notions of creativity in networks today is in painting or filling holes in images. Because if you take this image and decide to remove that lady over there and get that result, then there's a notion of Gestalt here. Who knows what Gestalt is? Okay, so just a little bit. I actually forgot to put the example, but yeah, but think of if you have, right, these two, then you see the line, right? You see the line going between my fingers, even though it's not there. So you see the curvature of the mountains and the sea and the sand, it's all there, and the network that filled this hole had to know how to fill it in the correct way. So it has a notion of Gestalt, which is a very important notion in creativity and in art. Right, just another little example. Oh, the contrast here is very low, but still in painting again. Now, the way I see it, again, neural networks and AI can help us, can augment us. They can drive the processes that we want to achieve in ways that we couldn't do before. So generative design and not just procedural design, because if a procedural design mechanism would be some system with a couple of parameters and I need to tweak those parameters until I get the thing that I want, then generative is already, again, sampling from that distribution space in ways that are not exactly structured like in a procedural design mechanism. So one of the better examples I know is from Autodesk, actually. It's called Project Dreamcatcher. And they use evolutionary algorithms and generative design to change the way you fabricate objects. You give you define your constraints, the constraints of the materials, the constraint of the object you want. Like a quadcopter has 4 blades, and it needs to hold up a camera maybe. And then you get, you generate all kinds of design, you explore them, you'll see the Pareto, and then you fabricate it. Right. So same thing, like this is one of the results they had in an article of how to change the whole structure of the bicycles just by the location of the handlebar. And it all is created by their system automatically. The user just picks a couple of constraints and you get that. And one of the better known examples, I think, from their project is actually a partition in an airplane. Partitioning, for example, the cabins from the business class and economy class. Then they needed a new partition, and they got all kinds of results. And you see maybe there's a Pareto front over there on weight and strength. And then they chose a specific model that was half the weight of the previous partition and twice as strong in external weight, taking up external weight. So this is in Airbus, it's in airplanes today. And also like water motion. So I can take this image and just animate it. And it happens if in one of our products in Pixaloop. It's a product that can animate still photos. So the user can usually just draw some motion field. But the thing is that water, it's not a constant motion field, it's time dependent. So even if a user wanted to create the mask of water manually and draw a lot of small arrows, they couldn't actually express this kind of stochastic time dependent motion. But we can create a model behind the scenes that does the segmentation and the stochasticity of the motion and just create this effect, right? So I'll run a little bit. And also content-driven or performance-driven effects. So this, there's no sound, but this is a video in Instagram and YouTube, you can find it. It was created by Ofir Shalom. He's an animator who worked tirelessly on this in After Effects by Adobe. And there are all kinds of examples of things like that in much lower quality than this. And when people ask, like, how did you do that? Then they tell them hours and hours on After Effects. But the thing is that you can take just any video. This is Yael, and she dances on command. No, just kidding. That's what her boss said. She's a choreographer, and she works in production in our marketing team. And that was very nice. But the thing is that if I take a person segmentation network that's suitable for video in real time and consistent, and maybe also a pose estimator, then I can get all kinds of effects with the press of a button. And right. So complex can become a press of a button with AI and algorithms that do all the heavy lifting behind the scenes. Also, tedious becoming effortless can come from simple segmentation masks and other algorithms. So sky replacement was a big hit in QuickShot, one of our apps. People seem to really like changing the skies in their photos. I mean, I was a big bettor on this because skies are a lot of times more than 50% of your image, and if they're not very interesting, then you want to put a little something into the scene. And doing this in Adobe Photoshop would be picking the lines, maybe using something better than the magic wand and getting a better segmentation mask. But I'll spare you. This takes quite a while, and this is X, I don't know what. And in QuickShot, it's a press of a button, and then you can go into more settings if you want to get the feeling that you control it. And you can see that not just the sky changes, also the ambience of the entire photo. And that's something that would have been very, very tedious to do. It was hard getting it to be production ready, and then we said, why not do it harder and do it in video? So we actually did it in video and published it in Eurographics. I talked about it in IMVC. They put a projector lighting me all the talk, so you can see me squinting there, but still. And right, it goes together. And also camera movement. So if I take this still photo and I want to create camera motion as if there's a virtual camera moving, then I need to know all kinds of things about the scene. Now, if I want to do it manually, I still need pretty sophisticated tools. I need After Effects, and I need plugins that let me create the depth map and then create the projections and interpolations and in-paintings that I need to do in order to create the scene that's moving. Again, I'll spare you the tedious work. And what we do, and it's coming soon, it's getting monocular from a single image depth map and then creating, again, the contrast here is pretty bad, but if you can see, it's moving in and out. And it's pretty simple. You can even play with the camera and change the motion. Right, a couple of other results. And finally, taking all that, when things become easier and you can do more, then you can get into maybe niche corners of design and art. Like, well, this is not, it's supposed to be green, but, and then it becomes, well, here's the glitter. But again, changing colors, it's a collaboration in Fashion Week that we did. There are results here. It's a combination of, again, a generative adversarial network and also like plain old computer graphics and rendering. This is work not from Lightricks, actually. It's SwapNet that was presented in ECCV. You take the clothes from one image and put it on a person in another image, not the same person. And as you can see, this is just again, and the resolution is pretty low, but the results are nice. And makeup transfer and other things that were never available before. And hair coloring, yeah, it's pretty dark. And retouching through sketching, you can just sketch a couple of constraints of how you want the shape to be or the color to be and get a result. Add jewelry or hair. Right? And before I go into one of the building blocks that we use to do all of the things related to people and faces, then I'll show you this specific use case of lighting, because you can take any photo and just add lighting. If you know what gel filters are, then lighting from different sources with different colors can create very distinct artistic effects. And this would not be possible without a model getting a single image and creating a 3D model of the face, of the geometry, and an estimation of the albedo, of the color of the skin, and an estimation of the lighting, of what is the lighting in the scene. So you can remove the old lighting, add new lighting, and do this. Right? And these are all before and after results. Again, it is pretty dark. Right. And for those who saw the Samson Russia paper, there are really nice things going in the, call it deep fakes, call it uncanny, I don't know, maybe. But taking a single image or a few pictures of the same person and creating a fully driven or drivable model of that person can get very interesting very fast. I mean, there are studios like Disney that instead of modeling really hard, all kinds of generated, rendered procedural models, just use these kind of things to generate a lot of avatars and a lot of stands, basically. Right. So I really want to be short on the short side here and have time for you to ask questions, but like this is a bit more of the technical part of how we do 3D face modeling today. And so maybe even stop me, like if there are questions, I'll run through it and then you can also ask at the end. Right, so basically from the mid-90s, I think, there were generative models, like active appearance models, that tried and find the correct model of the face by actually rendering, actually generating the face that the parameters you estimated told you to generate and comparing it to the face itself. It was very inefficient. It was a step-by-step optimization procedure. And generally, while results were interesting, the parametric models were not so good, and the the online optimization was very, very heavy to run and computationally intensive. And there were all kinds of advances, but the thing that's not written here is that actually neural networks are very good at learning optimization spaces ahead of time and then actually going through the optimization without actually calculating all the gradients and rendering the result at each step. On the other end, there are discriminative models that just tell you where things should be, like 3D meshes with a predefined number of points and fiduciary landmarks, predefined number of landmarks on specific points of interest, that you can try and regress if you have ground truth. You can try and regress them and get them to fit as best as possible. So what we did is in the last, I think, year and a half, alongside actually a couple of other groups in the world, is try to mesh these things up, because discriminative was nice. We had a model in the original facetune, but it required a lot of ground truth data, and it was very specific to just what it was fed. And if you take the disentangled representation of a face, you can think about it as geometry, illumination, and reflectance, or albedo, and then you can take those three and generate the rendered face, the overlay. And you see that the results here are pretty good. It's by Ayush Tawawi and Michael Zollhofer from Stanford, and really pioneered a lot of the work in that regard. And they got all kinds of very, very nice and interesting results that we actually got at the same time, kind of, and it would have been better to know about each other. But the thing is that it's why I call it a mashup, because you don't just try to regress the generated face like convolutional autoencoder, but you actually have a parametric model and you try to regress the parameters. So it's a bit like it's a mix between the discriminative and the generative. And you can generate something that's a lot sharper, but still, as you can see, also smooth on the skin. There's no noise. It is a bit synthetic looking. And I'll show you the results of how you can improve on that too. So basically, what you want to do is get some input, run it through a function, a model, a neural network that outputs parameters of the pose of the head, the shape, right, the identity, the albedo, okay, the appearance, the illumination, just the lighting of the scene, and the expression, which is, again, is geometry, okay, but you separate it from the identity or the shape, because the same person will have the same shape, for instance, in every frame of the video, but they can change their expression. And what you basically want is, again, to generate from all of those something that resembles the input as much as possible, which is the method of self-supervision. I'll go into that now. And what you can play with is network architecture, training corpus, and the loss functions. So, right. The training corpus, basically when you do self-supervision, is any picture with a person in it, okay? You don't need ground truth, you don't need any labeling at all. You just need a face detector, okay, to detect the faces. And self-supervision is very important. It's not just nice to have, it's crucial to have. I think that in a couple of years, we'll be rid of ground truth labeled data with all kinds of tools, not just self-supervision, but self-supervision is an important one. And to kind of tell you what you're seeing, it's actually a 3D graph where the points are on the price and ground truth, right? And the text itself is in the height of realism. So synthetic data, I can take Maya 3D or Cinema 4D and just generate a lot of faces. But it won't look like real people. And if I train a network on that, even though I know the geometry, I know the reflectance, I won't get something that works in the real world. You can do crowdsourcing, which is pretty expensive, depends on your solution. You can get quite a lot of it, but not as much as synthetic data. And it should be realistic. But again, it costs a lot. And you can use all kinds of other algorithms to reconstruct the parameters that are interesting to you. You can take videos where you can do structure for motion. You can take all the algorithms in the world, even if they take an hour per face, and run them and get reconstructed data, but then it won't be as accurate as some of the other results. And self-supervision is very cheap, okay? You can get as much of it as you want, and it's very, very real. Because, again, you're just trying to fit the actual appearance of a person. So that's basically the architecture from Tiwari's article in ICCV 2017. What they actually do is they also use a landmark detector, assuming it's a kind of a solved problem. It is, basically. And the image is input into an encoder network that the output from the encoder network is the parameters of the model. And then you use what's called a model-based decoder. It's a render pipeline, okay, for rendering the 2D image from the 3D model. And then you can just compare two things. One thing is pixel per pixel, how the face you rendered looks compared to the original input image. And the second thing, because the rendered face has a 3D mesh on it, okay, it has 3D points, you know where the 3D landmarks are, and you can also add a loss to the ground truth 3D landmarks. So it is important, the 3D landmarks loss, especially if you want to get specific things just in place, like the jawline or the corner of the mouth or things like that. So that's basically the architecture. I can tell you that while here they use AlexNet or VGG face as the encoder for the face, you don't need the heavy lifting monstrous neural networks here. You can use MobileNet, you can use any lightweight network that you want, basically. So the training actually kind of starts with a default naive face, right? So you get a straight looking default face, default illumination. The errors on the landmarks are pretty big, and I'll tell you about the last column in a second. And then the network begins to train, and it sees as many images as you can collect from wherever it is Creative Commons, right? But then you get stuff like that, because maybe the network didn't see enough images with large poses. Not everybody's looking forward at the camera. A lot of people are looking at the side, and it misses it. So you add more images like that. And then it gets results like that. We have all kinds of politically incorrect names for the squashed out faces, because the mouth is pretty important in the way it looks in the photometric loss, but the eyes are pretty fine sitting on the bags under the eyes and whatever. So you maybe increase the loss on the landmarks, and maybe it helps and maybe it doesn't. The thing is, it didn't always help. And what we noticed was that a lot of those images had hair, occluding part of the face. So the model that we know to generate only has a face in it. It doesn't have strands of hair. It doesn't have glasses. It doesn't have anything like that. So there are all kinds of solutions, like adding more vectors of albedo, of appearance, and stuff like that. But what we actually did is we taught the network what hair looks like, or where it is semantically, and told it to ignore hair in the photometric loss, and also all kinds of other occlusions like hands and microphones and whatever you can add to an image. So then you get these kinds of results. And it is nice, but it is still synthetic. So you can do a little bit of optimization. It got you almost all the way. And this is Zev, our CEO. And we get this overlay. It's pretty nice, but you can do 2 or 3 gradient descent steps, basically, and get that. So it is a lot nicer, and these are all kinds of results we got on device. It's basically just changing the geometry. The only thing changing here is the geometry, and then the lighting, right, in wrinkles also changes, and everything around it. Okay, so then you can get a model that looks like that, and you can relight it in a very realistic way and do all kinds of things. So possible use cases are many. I can really kind of run through them, and you can ask questions. Right, better relighting, we saw that. You can change perspective distortion. I don't know how many of you are aware of this, but if you take a selfie, right, then your hand is not that far. And the thing is that the tip of the nose or whatever is closer is distorted in a different way, perspective distortion, than what is farther away. Try and compare yourselves once when you take a selfie and once when someone takes a photo of you from afar. If the same size, if you make your head the same size, you'll see that in one of them you're kind of very wide and the nose is big, and in the other you look more like yourselves, basically. And also add makeup. You can draw makeup in the 3D mesh and just add it. This is very extreme, just to make the point. But you can just add it. Even to a video, you draw on one frame and get it in the entire video. Yep, okay. And the things you can do, again, with AI helping you, I think is pretty amazing, because we still have a lot of ideas and a lot of blocks, kind of blockades, all kinds of high thresholds of knowing very complex tools and taking the time to do the work. And if you can make all that simpler, if you can explore more ideas in the same time frame, then you can get to more creative stuff and create a lot more. And that's actually what our kind of agenda and what we're trying to do, and bring AI and creativity tools to all the people that we give our products to or sell our products to. And so this is my shameless self-promotion, right? If you have any questions, you can always reach me at my email, pretty simple, or ask here. Thank you.
Yeah, did you try to adaptate it for the forensic purposes? Because facial recognition is a big issue for mostly the defense industry, and also
Right.
So it's very useful because you can make a younger version or older version or the different version of.
Yeah, you can. Actually, the per vertex optimization finds the wrinkles. Once you find them, you can actually kind of stretch them.
Another big problem for current facial recognition technologies should see minimum 85% of the face if they are not using GPU processing system. Only in GPU processing system, maybe for the 9 pixel or very little pixel, they can catch it. So this system can complete the other part of this algorithm, maybe an embedded algorithm can complete the other part of this face, and then can create another very, very useful purposes. Have you ever tried about it? Or?
So we do create a full 3D model even from a partial face. If it's occlusions, if it's, again, because of extreme pose, exactly for changing the pose. A lot of times people look kind of to the side and they want to look forward. So we do that, and it works pretty well. To say that it's necessarily realistic, to say that I compared it to the real face that I have from another source, I didn't. You can from videos, right? It's pretty easy. But it'll probably work pretty well. We tend to be symmetric.
In what sense you mentioned that the self-training?
Self-supervision?
Self-supervision, yeah.
Right.
In what time you use it in your own system? I didn't get it.
So self-supervision is the fact that the input is also the loss. You use photometric loss, you just see if your output looks just like your input. So think of a tracking network that tracks backwards and then forwards and sees if it got to the same place. All it needs is to know where it started. It doesn't need any ground truth. It just needs to know where it started, and you know it.
The crypto network, you have like the bounding box, the features, you know?
So you have landmarks. You can train without it, actually. There are ways to train without the landmarks, but it just helps the training converge much faster. And getting accurate, not perfect, but accurate landmarks is pretty much a solved problem. It's really...
Okay, so that's classical kind of approach, and they train the network with classical approach?
So we actually also use a neural network to do landmarks, but classical approaches also work.
For question, all this cool stuff is enabled not just because of research advances, but because of hardware on our phones, right? It's getting better and better during the last years. Do you have right now some limitations, like you're waiting for better hardware to do more stuff, or you are okay with what we have now?
We've been working on neural networks on mobile devices for, I guess, 4 years now. And we used to feel alone, and then kind of Facebook and Google also joined the party. And it's usually just because, again, if you take inspiration from academic papers and you see maybe they got to some result, a lot of times it will be with VGG on a V100 running for whatever time. And then you have a small GPU on a mobile device with different architecture, by the way, that sometimes runs faster than the big heavyweights. But if you know the hardware, if you know the limitations, if you know the types of operations that work faster on a mobile device, then you can and go into methodical pruning and compression systems, then you can get to very fast and accurate results without waiting for newer hardware, just putting in the time to actually get there. For instance, this face model works on a device. We started it from something that ran, it took 50 milliseconds on a device, our own architecture, not the big like AlexNet or anything like that. And now it runs in 4 milliseconds on a device, and you can get there pretty fast.
But even 15 milliseconds is good enough, no?
Yeah, for real time it is good enough. But in painting, for instance, takes on device around a second to in paint, depending on the size of the hole. But it takes around a second. The thing is, the result is so worth it that users are willing to wait. But you can't run it in real time, right? So there are limitations, but we don't need to wait for better, bigger hardware.
And right now you are running on iPhone, right? Most of applications.
Yeah, most of the applications are only on iPhone. Some are on Android, Pixaloop, the animation of still images, and Facetune. Others are coming along the way.
I mean, how it's different for you, like, under the hood, what is running on iPhone versus what is running on Android?
Right, it is different. The frameworks we use to run them are different. The GPU languages are different because each one has their own thing. And again, in Android, there's fragmentation over different companies and different chips. But the basic idea, again, just networks are usually the easier part because you have a very well-defined architecture and maybe you need a different version for different hardwares or different generations, but it is well-defined. If you have a rendering pipeline after that, some image processing algorithms that are more classical and more involved in GPUs, then you really have to kind of implement everything.
Do you have some kind of algorithm to eliminate shaking? Because usually, because the camera shaking problems usually eliminates on the sterilized by DSP, digital signing processing system, and which is very expensive. Do you have this kind of solutions for? Because if you have, there's an amazing business approaches for you.
To eliminate camera shake just in general? We do, but it's not people are not that interested in it, actually. They just take that photo again. In dark scenes, if you saw Night Sight by Google, then it is interesting. But the stock cameras and hardware also are going that way anyways. So yeah. It's not a big feature. Cool. Anyways, I'm available. Thank you.